Welcome to the NetConf module. By the end of this module, you should be able to explain the NetConf protocol. Juniper developed the Junos XML management protocol, formerly known as Junos script, as an easy, reliable method of automating Junos devices. After using and improving Junos script for several years, Juniper worked with the IETF and shared it with the broader networking community. The solution was renamed as Network Configuration Protocol, or NetConf, and first appeared as RFC 4741. Support for SSH was added in RFC 4742. These RFCs were then updated in 2011 by RFC 6241 and RFC 6242. The real strength of NetConf is that it is a management protocol developed specifically for networking devices. NetConf can lock, read, modify, delete, and unlock a device configuration. It also has the ability to issue operational mode commands. Since NetConf is an IETF standard, it is used by multiple vendors, enabling organizations to use the same protocol to manage different vendor devices. The NetConf protocol is built specifically for networking and consists of 4 layers. The transport layer is responsible for creating sessions with network devices. The sessions can be established using the protocol shown. Junos primarily uses SSH. The messages layer provides a simple, transport-independent framing mechanism for encoding remote procedure calls or RPCs and notifications. The messages layer consists of 3 XML elements. The RPC element encapsulates all RPCs sent to a NetConf server. The RPC reply element encapsulates all RPC replies from a NetConf server, including return data and any OK, error, or warning messages. The notification element is a one-way message sent asynchronously to NetConf clients that initiates a create subscription RPC to the NetConf server. When an event of interest occurs that meets the specified filtering criteria, an event notification message is generated. Refer to RFC 5277 for more details on notifications. NetConf messages are used in all NetConf sessions to encapsulate NetConf operational commands and data elements. The operations layer defines commands that are used to perform operations on a network device. These operations layer commands are placed within one of the messages layer tags explained earlier. The different operations layer commands are as follows. Lock, which is used to obtain a lock on a device configuration file before modifying it. Unlock, which is used to unlock a configuration after modifying it. Get, which retrieves data from the running configuration database or device statistics. Get config, which retrieves the configuration from a device. Edit config, which is used to modify device configuration. Copy config, which creates or replaces an entire configuration. Commit, which commits a candidate configuration. Discard changes, which rolls back a candidate configuration to the current running configuration. Delete config, which deletes a device configuration file. Validate, which validates that the specified configuration can be loaded on the device. Create subscription, which creates a NetConf subscription for notifications. Close session, which gracefully closes a NetConf session. And kill session, which closes a NetConf session other than the one you are currently using. The NetConf content layer is where specific RPC parameters are encapsulated and sent to a NetConf server. The XML API provided by the Junos MGD process on the server accepts and processes the incoming RPCs and generates an RPC response that is returned to the client. The configuration data that you request from or upload to a Junos device is included in the content layer. One good feature of NetConf is that, other than the transport layer that is normally encrypted using SSH, all other layers are clear text, making the protocol easy to monitor and troubleshoot. To enable NetConf with SSH as the transport layer protocol on a Junos device, issue the Set System Services NETCONF SSH Configuration Mode command. Junos defaults to using TCP port 830 for NetConf over SSH connections. Some NetConf client applications use the standard NetConf TCP port 830 as specified in RFC 4742. To enable Junos OS to listen for NetConf connections on port 830, issue the Set System Services NetConf SSH port 830 command. Welcome to the Junos RPCs module. By the end of this module, you should be able to explain how to execute Junos RPCs using NetConf and the Junos XML API. One way to learn Network Configuration Protocol, or NetConf, is to open a NetConf session on a Junos device. All NetConf messages, operations, and content are text-based, so you can input them using the keyboard. Start a NetConf session using the Junos CLI by typing netconf while in the operational mode. Note that when starting a NetConf session, the username and corresponding Junos login class are displayed. Verify that the displayed user account has sufficient permissions to perform the required configuration and operational tasks. The same permissions are required for performing tasks using the Junos CLI and issuing remote procedure calls or RPCs using NetConf. Note that the Junos NetConf server displays its capabilities and the session ID. This information can be useful if there are multiple, concurrent sessions. Note the string at the end of the output. NetConf messages typically end with this string. Refer to RFC 6242 for more details on when this termination signal must be used. Juniper provides a NetConf XML Management Protocol Developer Guide. Here's an example to illustrate the execution of a Junos RPC using a NetConf session. The Get System Uptime Information RPC is equivalent to a Junos CLI Show System Uptime operational mode command. The results sent back from the Junos NetConf server are encapsulated in RPC reply tags. This is a well-formed XML document. Although it is not formatted using XML indentation, this output is generally processed by computers instead of humans. Note that according to RFC 6241, the RPC element should have an attribute named message ID, which is an arbitrary string chosen by the sender, typically a monotonically increasing number. This attribute must be returned in the RPC reply element unmodified. The Junos implementation of NetConf does not enforce the presence of message ID, so it is not present in the displayed output. This is used to ensure that responses are interpreted properly when multiple RPC requests are being initiated in a short period of time. Once a NetConf session is established, you issue NetConf RPCs that execute operational mode commands and modify the device configuration. All NetConf RPC requests are enclosed in XML element tags and end with the termination signal. The Junos XML API receives the XML formatted RPCs and forwards them to the Junos MGD process for execution. Junos CLI commands are processed using the Junos XML API in the same way. The Junos XML API returns XML formatted RPC responses from the MGD process back to the NetConf client. To find the equivalent Junos RPC for the Show Interfaces GE0/0/0 command, issue the Show Interfaces GE0/0/0 command with the Pipe Display XML RPC option. You should retrieve a reply similar to the one shown in the example. The Pipe Display XML RPC Junos CLI command option helps determine the correct RPC, but it is not the authoritative source. The authoritative sources are the Junos XML schema definition or XSD files released with each new version of the Junos OS. The example shows an operational data schema file. It shows that the interface name option is valid for the RPC in question. The schema definition files are useful if you have difficulties in determining the correct RPC using the Junos CLI, or if you want to see additional options. The Junos XML API Explorer is another resource to use in order to find the right Junos RPC. It is easier to read than the Junos schema files. It is also useful because it contains a description of each of the RPC elements. There is an XML API Explorer for operational and configuration tags. If you prefer to work with printed or PDF documents, you can download the Junos XML API Operational Developer Reference and the Junos XML Management Protocol Developer Reference Guide. You can use Junos XML RPCs to retrieve and modify device configuration. The example demonstrates the use of the Junos getConfig RPC to retrieve the contents of the Edit System Login branch of a Junos device configuration hierarchy. This example shows the data returned using the configuration request. Note that the response places the configuration data within data and configuration elements. The response also includes the Junos OS version, the date and time when the configuration was last committed, and the name of the user who committed the configuration. A similar process can be used to edit device configuration and to commit it. For more information about modifying configurations using NetConf, refer to the Junos XML Management Protocol Developer Reference Guide. Welcome to the Junos XML API Programming Languages module. By the end of this module, you should be able to list the Junos XML API programming languages. Extensible Stylesheet Language Transformations, or XSLT, and Stylesheet Language Alternative Syntax, or SLAX, were the first programming languages specifically designed to work with the Junos XML API. Starting with Junos 16.1, Python can also be used to perform the same tasks. Any programming language that can establish a network configuration protocol or NetConf connection, use the NetConf protocol, and send well-formed XML over that connection can be used to automate devices running the Junos OS. Juniper provides code libraries for multiple programming languages, including Python, Ruby, Perl, and Java. These free libraries make your interaction with NetConf and the Junos XML API easy. XSLT is a World Wide Web Consortium, or W3C standard language for transforming one XML document into another XML document. The basic model consists of an XSLT engine or processor that accepts as input a script or style sheet and an XML document. The XSLT engine uses the instructions in the script to process the XML document's hierarchy. The script identifies interesting portions of the XML document, how it should be inspected, and what XML output should be generated. Because XSLT was created to permit generic XML to XML transformations, it is a natural choice for both inspecting Junos configuration syntax and for generating errors and warnings. XSLT includes powerful mechanisms for finding configuration statements that match specific criteria. For more information about XSLT support in Junos, refer to the Juniper Automation Scripting User Guide. An example of an XSLT conditional logic statement is shown. In this example, when the hostname statement is included at the Edit System Hierarchy level, change the hostname to VMX1. Otherwise, issue the warning message, missing Edit System Hostname. XSLT is a standard programming language for manipulating XML, but it is not a preferred language for most programmers. SLAX is a programming language developed by Juniper engineers to make automating Junos easier. SLAX is now open source. One benefit of SLAX is that it is easier to use than XSLT. SLAX has the same capabilities as XSLT, and you can translate back and forth between the two languages. Actually, Slack's code is rendered into XSLT before being processed by the XSLT engine. Slacks is preferred by programmers who are not already accustomed to XSLT because Slacks enables the programmers to concentrate on the programming task rather than on learning a new programming syntax. Here is the portion of a Slack script that invokes the Junos Get Configuration Remote Procedure call, or RPC, on a local device, stores the output in the $results variable, and checks for the presence and value of a hostname in a Junos device configuration using Extensible Markup Path Language, or XPath, using XSLT instead of familiar if, else if, and else programming statements you would use when statements and create a program as an XML file. Slack's C or Java-like syntax is more familiar to most programmers. Slack's is widely used by the Junos automation community. For more information about Slack's syntax and capabilities, refer to the Junos Automation Scripting User Guide. The Slack's programming language, although similar to C and Java, has some limitations because of its close ties to XSLT. Junos OS Release 16.1 introduced native Python support, bringing the power of Python to Junos. The Python NetConf protocol library, as well as the Junos PyEasy library, are open source. Both are freely available at the GitHub website. You can access the website from the reference links document. Junos PyEasy builds on top of the NetConf library to simplify Junos automation as much as possible. The example Python script uses the Junos PyEasy library to connect to a Junos device and retrieve information from the device, known as facts, and prints the facts to the screen. The result of running the script is shown. Other tasks, such as viewing or loading device configuration, are made easy using Junos PyEasy. A big advantage of using Python for Junos automation is that the same language, libraries, and programs can be used for both on-box and off-box automation. Juniper Networks provides a Perl module, Junos Device, to help you quickly and easily develop custom Perl scripts for configuring and monitoring the Junos OS. The module implements a Junos Device object that client applications can use to communicate with the Junos XML protocol server. The Perl distribution includes several sample Perl scripts that illustrate how to use the module to perform various functions. The Junos XML protocol Perl distribution uses the same directory structure for Perl modules as the comprehensive Perl Archive Network, or CPAN. It includes a lib directory for the Junos module and its supporting files, and an examples directory containing sample scripts. The library contains several modules, but client applications directly invoke only the Junos device object. For detailed instructions on installing the Junos XML protocol Perl client and associated sample scripts, refer to the Junos XML Management Protocol Developer Guide. The NetConf Java Toolkit, which is available at the GitHub website, provides an object-oriented interface for communicating with a Junos NetConf server. You can access the website from the reference links document. It enables programmers familiar with the Java programming language to create applications that can connect to a Junos device, establish a NetConf session, execute operational commands, and create XML configuration hierarchies. There are 4 main classes in the NetConf Java Toolkit. Device, which represents a NetConf over SSH session to a Junos device NetConf server. NetConf Session, which creates RPC requests and processes the RPC replies from the NetConf server. XML Builder, which creates XML encoded data. XML, which contains XML encoded data that represents an operational or configuration request or configuration data. For more information about how to use the NetConf Java Toolkit, refer to the NetConf Java Toolkit Developer Guide. The Juniper NetConf Ruby gem is a NetConf library for the popular Ruby programming language. The NetConf Ruby gem, available at the GitHub website, provides classes and methods that enable Ruby programs to manage Junos devices using NetConf. It is installed using the gem install net netconf command. You can access the website from the reference links document. The source code is also freely available. The example Ruby script displayed connects to the target device and authenticates with the provided username and password. It does not perform any additional actions. In addition to the NetConf Ruby gem, Juniper also provides the Ruby Easy framework, which is built on top of the NetConf gem, enabling automation development without requiring specific Junos XML knowledge. Network administrators of Acme Core want to automate domain name system or DNS configuration on Junos devices, including routers, switches, and firewalls. Administrators need to view the existing DNS configuration and change the configuration to include a set of name servers. Acme Core's administrators are most familiar with the Ruby programming language because it is currently being used for server infrastructure automation. This case study uses the NetConf Ruby gem, but other tools could be used in a similar fashion. Before using the example scripts in a production network environment, avoid the hard coding of usernames and passwords for security purposes. Consider using SSH keys instead. Avoid hard coding device management IP addresses. Consider passing device host names or IP addresses as parameters when a script is executed. Add error handling to manage authentication errors, timeouts, and so on. Verify that the Ruby interpreter is installed on the control server. If not, install it using your favorite package manager. Install the Ruby Net NetConf gem by issuing the gem install net netconf command. In this example, an interactive Ruby interpreter, or IRB, is launched. The requirenet/netconf command returns true, meaning both Ruby and the net netconf gem are available. Since the solution uses off-box scripts, enabling netconf in the Junos configuration is necessary. The example script reads the DNS server configuration on a target device. The target device address and login parameters are defined in the login variable. Then a netconf SSH connection is established with a device object. Although detailed coverage of Ruby is beyond the scope of this class, the syntax of the example script is fairly intuitive. A Junos getConfiguration RPC is executed by calling the RPC method of the dev object, and the result is saved to the full config variable. Finally, the full config output is filtered using XPath, looking for all entries of system/nameserver/name and printing the name server list using the puts function. The final part of the task, provisioning DNS server configuration, is performed using the example script shown. It is similar to the previous script. The two examples could actually be combined into one script, but the example uses two scripts for simplicity. One difference between the two scripts is the RPCs that are executed. This example script uses additional RPCs to lock the device configuration. Load the new configuration using an XML formatted data variable called DNSConfig, commit, and unlock the device configuration. Existing DNS settings are removed using the nameserver delete equal to delete XML element.